Hello, welcome to our workshop, which is an introduction to 3D printing. We're Kuriosity Robotics, and I guess all three of us can introduce ourselves, and then I'll introduce the team. I'm Ethan Liang. I'm a sophomore at GCODE, but I'm here because I'm a member of Kuriosity.
I'm Reid Dye. Yeah, I'm also a sophomore, and yeah, excited to teach this thing.
I'm Arthur Balva. I'm a sophomore at Pali, and I'm on the build team for Kuriosity.
All right, so who are we? We're First Tech Challenge Team 12635. And so what's First Tech Challenge? It's a robotics competition that is put together by an organization called FIRST. And they have different levels of competition. And this is the most, like you can see in the bottom right, that's our image that's an image of our robot this year. And so we're given space constraints and have to accomplish a certain set of goals in the challenge. And so last year in the 2019 season, we were the NorCal champion and qualified for Worlds, which unfortunately was canceled. And so far this season, we are the holder of the world record currently. And so you can see on the bottom left an image of us last year, but probably more interestingly is a robot on the right. The top right is a render, a computer generated image, and the bottom right is an image of a robot. And so all the red parts you see on the robot are 3D printed. And so that's why we're here to present 3D printing, because it's such a powerful tool and can be applied so much. And so what are some applications of 3D printing? In the top right, you can see the intake of our robot, which is how we suck in the main element of the game this year, which are rings. And all the red parts you see, again, are 3D printed. You guys can see my mouse, right? Okay, let me put it on the pointer. And so this thing right here is 3D printed, and it's basically a two-in-one piece, which acts as both an axle that turns, driven by this, also 3D printed timing pulley, but also holds these polycord rollers that will pull the ring in also. And so we're able to do these two things in one part, because we've designed the part and 3D printed it. So 3D printing allows us to manufacture parts customly. But also, something else we use 3D printing for on the bottom left are our face shields. Over the summer, we designed and printed our own face shields, donating them. We've donated over 5,000 so far. And so the red part is the frame of the face shield that goes on your head, and that's entirely 3D printed. And so that's what we use 3D printers for. And so just like to get a gauge of what you guys know, or like how creative you guys are, what are some things you can think of that could be 3D printed? Like you can leave it in the chat or just speak up. All right. Well, so it's important to know that 3D printing is custom manufacturing, meaning you can make basically anything out of it. And so if you wanted like a chess set, you could print that at home. And so that's really the power of 3D printing. If you guys have any questions along the presentation, feel free to ask them. And I guess we'll just keep going for now.
So the first 3D printer ever was made in 1983, which is like a long time ago, but it wasn't really until 2010 that 3D printing became popular and widely available. And that's kind of weird, right? If it was possible to do back then, why didn't we popularize it? Why didn't we start using it? Because it had all these nice benefits. Does anyone have any ideas why this technology wasn't brought to the forefront of manufacturing till recently? Again, use the chat or say something. I see cost. It's interesting. Yeah, I'm seeing a lot of cost, which is definitely true. Advancements in motor technology have really helped. But really the biggest thing was the open source movement. In 2010, open source hardware started, which is this big movement to create open source hardware. It's pretty self-descriptive. And also the RepRap movement, which was a movement of open source 3D printers. And in addition to this, a bunch of key patents related to 3D printing expired in 2010, which really helped boost common, desktop 3D printing. Open source basically means that everything is open and the designs are free, so you can look at the plans and make one yourself. So it's not like the manufacturer is going to be like, no, you can't copy our design. Anyone can copy the design. And this really helps development because it encourages sharing and fast feedback and just helps development go faster. So many 3D printers nowadays are kind of standing on the shoulders of the open source giants, such as the first open source RepRap 3D printer, Darwin, which you can see in the top right, and also many early designs such as the Ramps mainboard, Marlin firmware, and some hot ends and heated beds, and we'll get to exactly what those mean soon.
All right, so we kind of covered this already, but if there's one thing you take away today, it's that the beauty of 3D printing is that we can solve problems in a few hours right at home. So with a 3D printer, we can manufacture any part that we can design right there in front of us, and it only takes some time and some filament. And so it's the perfect tool for both makers and people who just want to make projects in general. Like if you want a custom part, the easiest way to get it is through a 3D printer.
So let's dive into how these things work, right? It's a good question. They look pretty complicated, but they're really pretty simple when you get down to it. So 3D printing is a type of additive manufacturing, which just means it adds material instead of carving it away. And it uses that to make a 3D object. It's like a 3D pen, if you guys have used those. It squirts out hot molten plastic, and then if you control where the tip of that molten plastic is ejected, you can create a layer by layer structure that makes a 3D object. However, we need this to be very precise in order to create somewhat acceptable things from the 3D printer. So we use computer numerical control, also known as CNC, and this is just fancy talk for using a computer to control movement in space. So a key advancement, as I talked about earlier, was stepper motors, which are a type of motor that allows for very cheap and precise movement. So in order to print something, you generate commands for the printer from a 3D model, then feed those to the printer, and then the printer, it has firmware and a board, right? It tells the motors how to move in order to create the 3D printed part.
Right. So Reid touched base a little bit on what additive manufacturing is. But additive manufacturing is in essence the way that the 3D printer creates the object. So the 3D printer, it takes filament, which is basically just rolls of strings of plastic, and it feeds it through its nozzle. And the nozzle is really hot, usually around like 190 degrees Celsius. And so it melts this filament. And so you end up with liquid strands of plastic. And to create this 3D object, the printer will essentially slice the 3D model into super thin slices that it can print one layer of. And so it'll go around and print one layer, and then on top of that layer, it'll print the next one, and next, and next, and next, as you can see in that little GIF on the right.
So this is pretty important because it's the basis of how 3D printing works. Does it make sense? If you have any questions, you can ask in the chat or out loud, of course. Okay. Awesome. Very smart bunch. So basically a recap, but the filament is basically the most important part of the printer because it's what makes the product, right? And so let's follow the process again. sorry for the typo, but step one is you buy filament in spools, not spalls. And so on the top right, you can see an example of spools of filament. So filament is typically sold in strands, like Reid and Arthur touched on, and they're wrapped around in like big packages. Usually they're like a kilogram of plastic each. And then what you can do is what does happen is the filament is pushed by an extruder, and we'll get to what an extruder is later. But essentially that filament is pushed into a hot end. And so this image in the bottom right is an example of a hot end. This block of metal gets really hot. Like Arthur said, 190, 200 degrees Celsius. And so when plastic is pushed through it, it melts basically right away. And then as you're pushing the plastic, it comes out the nozzle in a strand of plastic. And then like Reid said, you just move where that nozzle is around in order to make layers and then put layers on top of each other. Okay. Since it's so hot and sticky, why won't it stick to the board? That is a really good question. And so usually so we call it the bed because that is usually heated also. And so, you know, advancements in 3D printing has allows us to get better and better beds. Essentially the bed is heated and it's in a special shape so that it has more surface area when it is warm. And then you print on it. And then when the bed cools down, it basically lets go of the part, it shrinks. And so it has less surface area. And then you can basically just pull the part off. And it's also, you know, there's some, I don't know what the material is, but there's some coating on the bed that makes it less sticky for plastic also. Yep.
I believe the plastic is called PEI. I'm not going to try to pronounce the chemical name.
Yeah. Yeah, but so the plastic is hot and sticky when it's melted, but after you put it down, the idea is that it cools and hardens to form a solid in place. So like you melt it to be able to shape it, and then it hardens in that shape. That's the idea. And so, you know, after you let your print cool, it won't be sticky. You can just pick it up and, you know, use it.
Okay, looks like we've got a question. How long did it take us to become comfortable with 3D printing? And advice on someone wanting to learn to use a 3D printer. So for this, we will get into this later a little bit, but mostly just advice would be spend time with it, try stuff out. You're going to have a bunch of failed prints, but that's okay. You know, these machines are not super reliable. If you want to learn one, there's lots of tutorials online, especially YouTube, but just get one and get your hands dirty, because, yeah. So now we know that we have to put the plastic down in a very precise spot, right? But how do you control movement of a print head to somewhere in three-dimensional space? You know, there's several solutions to this problem. The most common is the Cartesian motion system, which you can see in the top right, and yeah, just the images in the top. And in this system, there are 3 axes, which are they're just linear movement, and they can each be controlled by a motor. Now, 3D space can be described with 3 numbers, x, y, and z, right? So we have one linear axis for each number. By positioning each axis at the right distance or position, we can set the print head to a specific point in space. This is pretty much the simplest motion system to think about and to compute, and it's also the most common. However, it's not mechanically optimal. This is because there are so-called flying motors, or motors that have to move when the print head moves, and motors have a lot of mass, so that's a lot of inertia that we're going to have to move around, so that's less than ideal. And then also the bed has to move as well, right? You can see in the top left, the bed is moving as the y-axis, and that's really heavy, so that'll make your print slow down. Also, when the print head moves, it only harnesses the power of one stepper motor at a time, so that's less powerful. These problems are solved in other motion systems, such as Core XY and Delta. Core XY is like Cartesian, and it looks similar, but the bed only moves up and down, and the print head moves in X and Y directions. The motors are able to be kept still using some really complicated but clever belt paths. But another solution is delta kinematics. And delta is very different. They're mechanically the simplest to build, although they're really hard to think about and even harder to figure out how to move correctly with software. So there's a GIF in the bottom right you can see. Yeah, so all three motors work together to move the carriage, the center part. It's also called the effector in a delta machine, and neither the bed nor the motors move. This allows deltas to print much faster than Cartesians while maintaining accuracy. They're also good for printing tall things because the bed doesn't move, right? As you were saying, like the plastic does actually stick to the bed, so it's hot and sticky when it comes out and it sticks to the bed, and you want it to stick really well so it doesn't like fall over. But then when it cools down, it should release. However, this motion system isn't perfect either. It requires more computing. There's lots of square roots, and that's hard for computers and it's hard to figure out like, oh, if I want to move the print head to this position, where do I put all three of the motors, right? That looks just really complicated. So you need a more powerful computer to run it, and they also have to be built really precisely to be accurate at all. They also waste lots of vertical space because of the arms. So as you can see, there's a bunch of different ways to get the print head to move around to the exact place needed to print an object. They all have got pros and cons, and the one that's best depends on the requirements of the job, right? So if you want something fast, then you want a delta. If you want something that's like easy to tinker with or modify, maybe you want a Cartesian. Although I personally like deltas just because they look really cool when they run, but yeah. Right,
yeah, so some vocabulary that I think is important that Reid mentioned is carriage, which describes this thing right here that's moving. In the Delta printer, it's this thing right here. It's really small because the Delta printer is so large, but essentially that's where the hot end is. So that's where the plastic gets melted and pushed out of. And we'll talk more about the details of the carriage later, but essentially that's what we're talking about that has to move, right? And yeah, I definitely agree that Delta looks cool, but obviously it requires more computing. It's harder to visualize than the Cartesian printer. Any questions here? Awesome. All right, so now extrusion is the act of pushing the plastic through the hot end where it melts. And so there are, two main ways to extrude. So at the baseline, both use what is called an extruder. And so we have two images of extruders here. This is an actual extruder, and this is a diagram. If you look at the actual extruder, there's this, gear. There's this thing that looks like a gear here, and it rotates. This is a stepper motor, and it rotates this gear. And essentially the filament goes through, one end and it goes out the other. And this gear has teeth in it, and it pushes the filament by rotating. You can kind of see the diagram here. The green thing is the filament, and the gear rotates to push the filament. Hopefully that makes sense. And so there are two different extrusion systems. One is called Bowden, and one is called direct drive. And so the difference between the two is where this extruder is. So if you look at this top right image, it'll show you exactly the difference. So in a direct drive system, in the left, where my mouse is, the extruder is directly above the hot end in the carriage. But in a Bowden extrusion system, the extruder is separate from the carriage. And so if you look at this printer, the Anycubic printer, the filament goes through here to the extruder. This box right here is the extruder, which is pushed through a tube called a Bowden tube to where the hot end is. But in this printer, there's no such thing. This is a filament sensor to see if there's filament existing or not. But what pushes the filament is actually on the carriage itself. So the plastic is pushed directly into the hot end here. So, why would we use a Bowden system? Why would we prefer pushing it from further away? And so the reason to doing that is that this whole chunk is offset. This extruder is actually quite heavy. And when we put it separate from the carriage can move more nimbly. It's also less heavy, so there's less inertia causing vibrations. So generally prints are cleaner. But the benefit of direct drive is that there's no distance between the thing pushing the filament and where the filament is getting melted. So there's no play. And sometimes this long tube, the filament can get stuck inside of it. which also presents a problem. So you get more responsive because it's right there. You're pushing directly to where you want the filament to be. It's more responsive, there's less play. So that's the benefit of direct drive. But again, Bowden allows for less weight on the carriage. And so how you choose depends on experience and personal preference mostly, and your application. So are there any questions on this slide? All right, I think we're almost, we're pretty far along the explanation process. So which one is more common? That's a very good question.
Well, I mean, it depends. It depends what market of printers you're looking at. The more often, like cheaper printers you'll get, all have Bowden systems just because they're cheaper and you don't need to have as rigid of a machine to handle, because you don't need to handle that extra weight. But more expensive machines can also have Bowden systems. Like the first kind of pioneer of the Bowden drive system was a very high-end machine called an Ultimaker, and that prints very well too. So they're kind of both very prolific, and it depends, basically. That's kind of the answer. It depends. All right. So we've covered how printers work mechanically, but what if you want to actually print something, right? That's kind of important. So 3D printing may just seem like, oh, you just tell it to print and then it makes your thing for you. But there's lots of limitations, right? Additive manufacturing does expand our manufacturing capabilities greatly because, it can create a whole bunch of geometries that traditional like milling or machining can't. But there's also a lot of problems with it. Like, because the filament is hot and kind of liquidy when it comes out, you can't just like print horizontally and expect it to stay there. It's just going to fall. And you can't print like an upside down U. Like if you had like a J, upside down, one side of it would kind of be floating in midair. So, you need to fix that. So in order to fix that and the problems with overhangs, because, overhangs, they sometimes drop down, as you can see in the photo, we put supports on it. And this just is extra waste material that you have to take away afterward. And then that helps support the part while it's being printed. So you can see in the bottom right, these structures were printed without support, so they all sag down and look really bad. Another problem with 3D printed parts and 3D printing as a process is that, it's not very accurate. Like with the heat expansion and contraction, you can't really judge how much parts are going to change in dimensions once you print them. So you do need to add tolerances when you design things to make sure that they fit together. Finally, you have to make sure that your part will stick to the build plate. Someone said earlier, right? You can't have just like one tiny little point that's on the build plate and then expect to print up from there, because then it's going to fall off, and that's bad because, then your print will fail. So, yeah, some ways of making parts easier to print while you're designing them is to create some support material of your own, because 3D printers, while they may not be able to print horizontal, like in the photo, if there's two vertical supports and you bridge across them, they can do that. So that's very good. And the material dries fast enough that you can bridge across. So the average, I see there's a question in the chat, the average time for the plastic to cool down it really depends, again, because sometimes you're printing with very, very high temp materials around 400 degrees Celsius, like PEK engineering plastics, and those will take around like 30 seconds or so. And it really depends because like sometimes you put a printing fan on it to make it cool down faster so you can print steeper overhangs, but sometimes you don't want that because it'll cool down too fast and then the thermal contraction will cause the part to warp. So yeah, it depends. Sometimes it can be like 1 second, and sometimes it's like 30. Yeah.
Yeah, the most commonly used plastic by hobbyists that we use is called PLA plastic, and it tends to cool within a couple of seconds.
Yeah.
So that's pretty good for bridging because, especially if you have a fan on it, the idea with overhangs is that you want your layer to cool fast enough that it doesn't have time to fall over. And so the faster your plastic cools, the less it can fall over.
Mm-hmm. Exactly. And we can mitigate problems like overhangs by using like kind of flat chamfers, like where you'd round an edge instead of rounding it, you just cut off the corner, so it's still kind of rounded, but it's still a 45-degree angle, which printers can't reproduce. And that's like another thing. You know, a sphere is a pretty simple object, but you can't really print a sphere because there's no surface area on the bottom, and you know, there's a super steep overhang there. So spheres are really hard to print. So those are some limitations in how you should design for printing. Okay, so once you've designed your part and you're confident that you can actually print it, you have to export the model into a program called a slicer. The slicer will take the model and make it into instructions for the printer. We'll go into that a little later. But the slicer only takes this file format called STL. And this might sound like it's not very important, like you just convert it, but it is, right? Because an STL is a file format that's the model, but only in triangles. So you can see the left would be like how you'd see it in your CAD program, and the right image would be the STL file. So does anyone have any ideas on why we might want to segment it into all these little flat triangles? Anyone? You can even just talk. Yeah. I see. So I'm seeing because flat chamfers give more support or are easier to print, because that way it's easier to hold, like on the bed. So yeah, these are good. I might have to clarify something. So normally you'd have lots and lots of triangles, like 10,000 triangles representing your thing. Someone needs to be put in a breakout. So it doesn't really change the geometry of the object very much. So yeah, it doesn't really help it make it easier to print.
Yeah, usually STLs have so many triangles that the printed object basically looks like in this instance, the printed object would be close enough to a sphere. Like you wouldn't be able to see that there are triangles on its surface.
Yeah. So I'm seeing more smooth surface, which is, you know, you can't really tell, but it is actually making it more bumpy. If there's a host, I think someone's asking to join the Chrome breakout room.
Yeah, I'm trying to fix that right now.
Yeah. But the reason why we do this is because, you know, you can't really tell a printer to move in a curve, right? How are you going to tell the x-axis motor? You should turn over, your speed over time should be proportional to a sine wave. The motor's just going to look at you like, I have no idea what you're saying. You have to tell it, move at this speed, then for 1 millimeter, then move at this speed for another millimeter. So the STL file is a way of segmenting up the object into a bunch of little tiny linear moves that the printer can understand. And yeah, that's why we change things to STL format.
I actually can't see the, sorry, I can't see the chat right now. Can someone tell me, like, which breakout room that person wanted to join?
Anthony would like to join the Chrome extension.
Okay, thank you.
So we got a question in the chat that says, why not square? So there is a file format that is square, and it's called OBJ, and we can use that too, but squares are just harder to work with than triangles, because 3 points will define a plane. So it's impossible to have a triangle that's not 2D, but it's impossible to have a 3-pointed shape that's not 2D, but it is possible to have a 4D shape, a 4-pointed shape that's not 2-dimensional. And then if that happens, then it causes problems for the slicer, and it doesn't really know where the surface is within those 4 points.
All right, so we can't just send the STL file to the printer and expect it to know what to do, because the printer doesn't understand 3-dimensional objects. So what we do is we need to send our STL file to our slicer, which we'll talk about in the next slide. And essentially what the slicer does is it converts the STL file into GCODE. And GCODE is essentially just a bunch of code that describes and tells the motors like a set of points and like movements. And so the motors individually know how to move in order to create that 3-dimensional object. And so typically what you would do is you would just put in the slicer and the GCODE will get sent out and you can just plug that into the printer. But if you're some advanced 3D printers, or if you're really advanced with 3D printing, you can sometimes even edit the GCODE. So for instance, over the summer in our face shield initiative, once we sliced our print, we wanted to basically repeat the print over and over again and have the printer knock off our prints automatically by itself and then start printing the next one. So you can actually technically go into your GCODE and edit your GCODE if you know how to write in GCODE.
And another note about GCODE, sorry, before you move on, is that it's not like a normal coding language. It's super simple. Like the most common command is G1, and it's just go to point. So you'll see just a file that's thousands upon thousands upon thousands of G1, 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 G1. So it's not like, you know, loops and ifs and things like that.
Okay, so the slicer. So as I just mentioned, we need the slicer in order to take the STL file and transform it into GCODE for the 3D printer. And so there's a lot of different slicers. Most common ones are usually Cura or Prusa slicer, for instance. And essentially what they do, as you can see in this image, they take the STL file and then cut it up. The slicer, as you can tell from the name, just slices the STL file into little layers so the printer can print. And based on those little slices, it'll create GCODE for each layer. A question in the chat? Oh, okay, never mind. You think we should go to the next slide? Cool. So in the slicer, there are probably hundreds of different settings that you can find. But typically in a slicer, you actually choose what printer, like generic printer settings. And with those settings, most of the settings are already finely tuned. So there's typically only 3 settings that you need to change. So the first one is layer height. Layer height basically affects how thick each layer of the 3D print is. So as you can see in that top right photo, the one on the left has the smallest layer height, and the one on the right has the tallest one. And so having a taller layer height can allow you to print way faster, essentially like 3 times faster than if you have like a layer height that's 3 times smaller. But the issue is that if you're printing surfaces that aren't vertical or aren't horizontal, you lose a lot of accuracy or smoothness essentially. So you can see, like, in theory, the STL file is perfectly smooth, but with a pretty thick layer height, it's basically a bunch of steps, right? A bunch of steps, and it's not very smooth. And the smaller your layer height is, the smoother that surface can be. And then the next 2 settings are all about infill. So infill is basically the structure inside the print. And so printing the outside structure, the outside surfaces of the the STL file are pretty simple, right? You just need to know where to print, but you can't just print the outside surface because once you get to the top or like cover it, it'll just collapse. And so you need infill inside the print in order to support the other structures. And so the first setting is infill pattern. So you can see in this middle photo, there are several infill patterns that you can choose from. There's some more generic ones that most people use, but usually they don't really matter which infill pattern you choose. It's more about your personal preference. And then infill density is basically how dense that infill is. So obviously the lower it is, the lower your infill density is, the weaker the print will be, and the higher it is, the stronger it will be. So you can see like the 0% infill is like no infill. 50% is about like 50% of the print is filled in, and 100% is the whole print is filled in. Typically, when 3D printing, if you want a really strong structure, you don't typically actually have to go to 100% infill. Most of the time, the max infill you'll use is maybe 50% infill, because at that point it's so filled in that it doesn't actually lose any structural integrity.
It looks like we've got a question in the chat about G-code. Go there. So the question is G-code written or used on SolidWorks, and does it work on every CAD software? Is it software specific to the 3D printer? So G-code is not written or used in SolidWorks. SolidWorks is the CAD program, and the CAD program makes the model, and then the CAD program exports the STL file. Then you take the STL file and you import it into the slicer, and then the slicer slices it up and then makes all the commands, and then the slicer writes the G-code commands. It's kind of like how the C compiler writes assembly for the machine to follow, right? So G-code is kind of universal to every printer, and so you can slice it, and then the slicing, and then that sliced file will be a G-code file, and then the G-code file is the instructions for the printer. I hope that makes sense. Does it make sense?
Yeah, and the purpose of using this format called G-code is that over time, most 3D printers, I'd like to say all 3D printers, agreed that we'll use this type of command structure, this like G1 means to move to a point. Everybody basically agreed to use that for every 3D printer. All right. And so the results of, CADing and then slicing and then all that work, and the result is we can print anything we want on the 3D printer. So you can see a batch of 4 face shields on the left side. On the right side, this is the printer printing a single face shield, which it'll later knock off the bed and start over again. Can you stop the machine by code, or do you need to stop it by pressing a button on the machine? I'm assuming that's like if you want to stop it in the middle of a print, every machine will let you to press a button to stop it. There are G-code commands to wait, whether it be for a specific temperature or for a specific amount of time. We use the temperature wait to be able to, wait until the bed cooled to knock over the print before starting the next one. And so there are different G-code commands that we can use to wait, but usually it is, you stop on the machine and it'll stop printing.
Yeah, and when the print's done, it'll just stop itself, right? Because it ran out of commands, finished the code.
Right. Yeah, and so I guess we forgot to mention, G-code is usually like the slicer spits it out onto your hard drive, and then you take an SD card to transfer it to the machine.
And then the machine just reads the G-code file. So yeah. Now, if you want to do this, you can choose any kind of level of printer, right? So there's all kinds of levels, and it's really based on what you want. 3D printing is so much cheaper now than it was, and so much more accessible. In 2010, printers would be like, I don't know, $1,000 or $2,000. So this is really a step forward. You can get a really good printer. The Ender 3 is really good for just $200. But if you want the comfort features of flexible beds, filament runout sensors, and things like that, you'll have to go for little higher prices. But still, these things are very, very common, and these are just a few that we recommend. Ender 3, Anycubic i3 Mega, and the Prusa Mark III. This one you'll notice is a lot more expensive, but it is definitely higher quality and higher, it's just a better user experience. If you want to get into printing as a hobby and you want to modify your printer and make it, kind of the best, most upgraded thing possible, then you might want to get the Ender. But if you just want to use it as a tool for your creativity, then you should probably get a Prusa. And looks like we've got a question about if the plastic in the machine, or does the plastic come with the machine, or do you have to buy it yourself? I think that's the question. So some nicer machines like the Prusa do come with one roll of filament, so one probably kilogram. But after you use that up, you do have to buy it, and filament is around $20 to $25 per kilogram. So that's one of the reasons why we don't print with 100% infill, because that's expensive. If you print with 20% infill, things are still quite cheap and strong. So yeah, you can sometimes get it.
A kilogram of filament is actually a lot. For a robotics season, I don't think we burn through a kilogram per year. But if you're going to be mass producing, like we were making face shields hundreds per day, 120 per day, sorry. And so that meant we had to burn through spools and spools of filament. If your printer is running 24/7, you would use a lot of plastic. But for a hobby, you could print an entire chess set and would use less than a 20th of a spool, so.
Yeah.
All right, so I've put Ender, Anycubic, Prusa in the chat. Prusa is the most expensive because it has all these features. Basically, you plug it in and it works. You don't have to tune it. The Anycubic has features like filament detection. We got quite a couple of these. I personally enjoy using them. Maybe it's just because I was introduced to them. That's my 3D printing introduction. But they, it's cheaper, so you'll have to work with it more hands-on to fix it sometimes. And so the cheaper you get, the more you'll probably end up having to fix it by yourself.
Yeah, and this does bring up an important point. 3D printers are not yet at the point where it's kind of plug and play is assumed. They're going to break. You're going to have failed prints. And the more you spend, the less of a chance there will be, generally, that might happen. But it's probably still going to happen because this is a new technology. I mean, we've only been seriously developing it for the past 10 years, which is, nothing in the scope of development of things like light bulbs and cars. Yeah. So, got a question. How do you connect the machine to your computer? Is there going to be a line thing? So, you can run printers in two ways, connected to your computer and from an SD card. So if you connect to your computer, then your computer sends G-code over a USB cable to the printer, and that works great. And the other way is you can put the G-code file on an SD card, put the SD card into the 3D printer, and then have it just read the G-code from the SD card. And that's what we've been using for our robotics team. Yeah, so now we know we can print things, and this is great. There's tons of free models available online in huge repositories like Thingiverse.com or My Mini Factory or Umagine, or there's a lot of files online. But what if you want to design a custom part? Like if you need something to fix this niche little part that broke in your house, then what should you do? Then you need to learn a CAD program. CAD stands for Computer Aided Design or Computer Assisted Design, whatever you want, just not Cardboard Aided Design. That's very different. So we, for robotics, use Autodesk Fusion 360. By the way, all the programs I'm mentioning are completely free for hobbyists because we're cheap and we don't want to spend money on it. And these are really good programs. Like Fusion has built-in stress simulation for free. But if you don't want to use Fusion, there's also Onshape, which is just Fusion, but it's on the cloud, so it doesn't take very much computing power on your computer. And there's also things like Tinkercad, which is really great for beginners. It's very visual and, you know, kind of drag and drop kind of thing, and it's really good. But if you're more into making kind of organic shapes and sculpting and things like that, then you might want to check out Blender or Mesh Mixer, because those take in just STLs, and then you can manipulate the parts and the points and the triangles, and that will let you make more organic and bendy and smooth shapes. But the main thing is you just have to practice. Practice, and you'll get really good. Like, this is a render of a car that we made over the summer. It doesn't work, it's just a CAD of one. Also, if you're a big, like, hardcore programmer, I mean, I guess if you're here, you might be, you could check out OpenSCAD, which is kind of a code-based CAD program that might be more familiar to you, but for most people, I tend towards like Fusion or Onshape. So.
Yeah, so I mean, the best way to learn CAD is to just choose the software and get into it through online videos. There's online free classes. Or, I mean, if you wanted to, you could try to attend a class with us. So Reid mentioned that we did the cars, and that's from a class. Like, obviously through the season we CAD more serious things, but this was just like messing around in our class. We were able to learn how to render, how to CAD. And so personally, this is really doable if you just learn online. But I think we are going to put together some summer classes if you're interested from learning from us specifically. And so the workflow to learn CAD is to choose a software, to learn, to practice, and then to create. And while you're practicing and creating, you'll be like, oh, how do I do this? Well, then you can just go Google it, and then you learn how to do it. And so in that way, you get more and more experience. All right.
Right, and that's the end of our presentation. If we've got some more time, we might want to do a demo of just the whole workflow of printing.
Do we have time
for that?
Yep. We'll give you about 5 minutes.
Okay, I can do this.
Speed run.
Speed run.
Do you have Fusion open? If not,
I do have Fusion open.
Okay, awesome. All right, I'll stop sharing my screen. So we'll show you, converting from a part in Fusion and then exporting it as an STL and then putting it in a slicer.
So you can see I've CAD'd this amazing muscle car. You can see why I named it that. It's a play on words. And so I'd want to print the car and the muscles separately. So we're gonna hide the car, and then let's see this muscle thing. We're going to take this component, right? That's this whole thing. And go to the body. You can see this. It's a mesh body. And let's see, show it. Uh-oh, that one's really small. Okay, we're not going to be printing the muscle. You can see there's lots of problems with this. And yeah, there's always problems. Should we print? What do you guys want to print?
Just print the car without the muscle.
This one? Okay, print this one. Let's see, we have to find the body. Oh, wait. Aha, I found the muscle. Okay. We're going to save it as an STL. And what this does is it converts it to an STL just like before. And here I've selected that it's going to send it to my slicer app called Prusa Slicer. So I'm going to click OK. And this is a great model. I chose this muscle model because it has it's nice geometry, and it's going to be hard to print, right? Like, how do you find a flat space on it? So here's Prusa Slicer. You can see we've imported this, and we're going to want to put the flat part down so we can orient it down on the bed. And you'll notice, how is it going to print that, right? That's printing in midair, so we need to turn on supports. So it's going to, so this is what, you'll see that popped up. That's the reason that this Prusa Slicer is so good. it was made by Prusa, but it's still open source like I talked about earlier, so anyone can improve on it. And that's how we get these nice features, like it reminds you, oh, you should turn on this feature if you're going to use support. So that's what I just did. And I'm doing it on, let's see, ultra detail. See another one. And you'll see that this is just the layer height. So that means that it's going to be really fine and it's going to look really smooth. I've set it to PLA, which is the plastic that Ethan was talking about that's really common. And this is my printer profile. You see the infill is 20%, which is really plenty. I'll go to the layer view. You can see that there's support material here. It's supporting it where it needs it. And you'll see all the layers, and there's the infill inside. And that's how the printer's going to print. So now we're going to export this G-code. Actually, yeah, export this G-code. I'll send it to this file. I'm going to rename it. There. And then we can go to, so I just exported it, and I've got this software on a Raspberry Pi called Octoprint, and it's running this server, and it's going to stream, and it's just working like a normal computer. It's going to stream G-code through the USB, like I talked about earlier, to the printer. So I can upload a file and go to 3D printing, print files, and you'll see the file that we just exported. We can upload it. And while that's uploading, let's look at this. Let's open it with where's Sublime Text?
You can just use Notepad.
Okay, just use Notepad. So you'll see that there's a bunch of, these are comments, and then there's M codes, which are just G codes with M. Don't ask me why. These are setting the temperature, waiting for things to happen, like to warm up everything, because it takes a while. And then you just start seeing G1, and it's just going to place, going to place, going to place, over and over and over for a long time. And then, once I'm in here, I can just click this, and then click print. I'm not going to print it because I don't have filament loaded in the machine, and we're out of time to go show how to do that. But yeah, that's the workflow. So,
yeah, hopefully you enjoyed our introduction to 3D printing and this last, crash course demonstration of the process. But hopefully you've learned more about printers and stuff. I'll leave some contact info in the chat if you want to contact us. And otherwise, you can ask questions in the chat or email us, and we'll answer them. Yep. And thanks for the time, TeenTech.